Hey everyone, today we're going to dive into the hidden science that turns a boring old rock into the shiny metal in our buildings, our cars, and even in our pockets. It's a field called metallurgy, and honestly, it's a fascinating story that starts deep, deep inside the earth.
I mean, have you ever really stopped to think about it? We don't just dig up sheets of aluminum foil or find chunks of titanium ready to go. They all start their lives chemically locked inside what looks like just ordinary rock. So how in the world do we get from a piece of the earth to a high-tech component? Well, that journey is exactly what we're going to explore. So that entire process, from the moment a rock is pulled from a mine to the point it becomes a finished product, that's metallurgy. It's this amazing mix of geology, chemistry, and some really clever engineering, all focused on one single goal: pulling pure metals out of the complicated stuff they're trapped in. Okay, so let's start at the very beginning, deep underground. Because the metals we value, like iron or aluminum, they aren't just sitting there waiting for us. Nope, they are chemically bound, trapped inside different minerals that make up the very rock we're standing on. Now, when that rock gets mined, it's basically two things all mashed together. You got the ore, that's the good stuff, the mineral that actually has the metal we want. And then you have the gangue. That's just all the other junk attached to it. Think sand, clay, and other worthless bits of rock. The first big job is figuring out how to separate them.
And this is a massive challenge. I mean, a lot of the time, the valuable ore is just a tiny, tiny fraction of everything that's been mined. Trying to process all that useless gangue would be a colossal waste of time and money. So before we even get to the chemistry, we have to find a way to concentrate the ore.
And this is where the clever engineering comes in. They've got some brilliant tricks for this. For really heavy ores, they can use gravity separation. It's kind of like panning for gold, where they wash away the lighter gangue. For other types, they use this incredible process called froth flotation. They whip up an oily froth that the ore particles stick to, and it just bubbles right up to the top. And if you're lucky and the ore is magnetic, it's even easier. You just use a giant magnet to literally pull the good stuff away from the junk. All right, so we've sorted the good rock from the bad. Our ore is concentrated. Now we can finally get to the main event, the chemistry. We've gotten rid of the physical clutter, but our metal is still chemically stuck to other elements, usually oxygen or sulfur. It's time to break those chemical bonds for good. The first chemical step is usually converting the ore into something called a metal oxide, which is just easier to handle in the next stage. There are two main ways this happens. For ores with sulfur, we use roasting. You heat the ore with a whole lot of extra oxygen. For others, like carbonates, we use calcination, which involves heating them up really hot, without any air. Both roads lead to the same destination, a metal oxide.
Okay, this is the moment of truth. We have our metal bonded to oxygen and we need to break them up. So how do you do it? Well, you introduce a third wheel, something that oxygen wants to bond with even more. That's what a reducing agent does. Very often, it's just simple carbon. You heat them all together, and the carbon basically swoops in and steals the oxygen, leaving our metal, finally, free.
So how do scientists pick the right reducing agent? They're not just guessing. They use thermodynamics to figure out exactly what's going to happen. This rule you see here basically says that for a reaction to happen all on its own, it has to release energy. Think about a ball rolling downhill. It doesn't need a push, it just goes. It's a spontaneous process. This principle lets scientists calculate which element will win the fight for oxygen at any given temperature, making the whole thing super efficient. So we've done it. We have our metal. But hold on. It's not quite ready for your phone or a jet engine just yet. This crude metal still has tiny bits of other stuff mixed in. For the really high-tech applications we rely on today, you need extreme purity. And that final step is called refining. And some of these refining methods are just unbelievably cool. Take the Van Arkel method, which they use for metals like titanium. You start with the impure metal and you heat it with iodine, which turns it into a gas, leaving all the solid impurities behind. Then that gas drifts over to this incredibly hot tungsten filament where it breaks down and deposits a layer of ultra pure titanium. It's just this elegant chemical dance to get to near perfect purity. Okay, so we've seen all the modern, high-tech science, but here's what's truly mind-blowing. The core ideas we've just talked about, separation, reduction, dealing with impurities, were mastered by ancient metallurgists thousands of years ago. And they produced some results that, honestly, still baffle us today. 1,600. What does that number mean? Well, think about a piece of iron. If you left it outside for 1,600 years, what would you expect to find? A pile of rust, right? Maybe just a reddish stain on the ground. But not in this case. This is the Iron Pillar of Delhi. It stands almost 24 feet tall, it weighs more than 6 tons, and it has been sitting out in the open through monsoons and scorching heat for over a millennium and a half, and it hasn't rusted. How is that even possible? After a ton of research, scientists think the secret is this incredibly thin protective shield that formed on its surface. It's a special compound of iron, oxygen, and hydrogen that basically stops rust dead in its tracks. It probably wasn't even intentional. It was likely just a happy accident, a result of the unique materials and the specific forging methods that the ancient craftsmen used. The Iron Pillar is just an incredible reminder that this journey from rock to remarkable is a story as old as human civilization. It's a testament to unbelievable skill, and it leaves you with this really fascinating question. What other secrets from our technological past are still out there, just waiting to be understood?